Before we start building deep neural networks, we need to understand their most basic building block, a simple linear model. The goal of linear regression is straightforward. We want to learn a function that maps an input feature to a continuous numerical target. This mathematical derivation shows we can solve this problem using calculus and linear algebra. By minimizing mean-squared error, we calculate a closed-form analytical solution. Looking closely at the bottom equation, solving for parameters requires calculating the matrix inverse. This scatter plot shows the result of that math. Applied to a simple set of two-dimensional data, the normal equations give us the exact slope and intercept to fit a perfect line. But relying on this analytical approach has a major drawback. Computing the inverse of a matrix is incredibly expensive. As datasets scale to include thousands or millions of features, that calculation becomes slow, highly memory-intensive, and mathematically unstable. To build machine learning models for modern datasets, we have to abandon closed-form matrix math. We need an automated, iterative process to estimate parameters instead. This network diagram illustrates how we translate the regression problem into PyTorch. We start with the simplest possible architecture, a single neuron mapping an input feature through a trainable weight parameter. During the forward pass, the network multiplies the input by that weight to generate a predicted output. It then compares that prediction against the actual ground truth to calculate the error, or loss. Then comes the backward pass. PyTorch automatically computes the gradient of that loss and uses it to update the initial weight, nudging it closer to the correct answer without requiring us to solve any complex calculus by hand. This flowchart breaks down the actual code workflow required to run those passes continuously. For every training cycle, we reset the gradients to 0, calculate the loss, run the backward pass to compute new gradients, and finally step the optimizer to lock in the parameter updates. PyTorch acts as an engine for automating calculus. It takes the theoretical math of gradient descent and turns it into highly efficient executable code. But look at this scatterplot. The line our single-weight PyTorch model produced completely misses the overall trend of the data. Because the model only learned a single parameter, it is artificially anchored to the bottom left, forcing it to cross exactly through the 0-0 origin. Think back to the basic mathematical equation of a line. Based on that rigid origin constraint, what specific parameter did our model forget to include? We missed the bias term. This updated diagram shows the network with a new, independent parameter representing b. By explicitly setting our model to include a bias, we give the network an independent value that feeds directly into the summation neuron, allowing the entire line to shift vertically off the origin. This corrected plot shows the result. With the bias parameter properly calculated and applied, the fitted line shifts upward and tracks exactly through the center of our data points. Writing PyTorch code without understanding the underlying math turns the framework into a black box. You have to dictate the architecture based on the mathematical requirements of the problem. Now, look at this scatterplot. The data follows a complex wave pattern. A standard straight line has no chance of fitting this curve. To solve this, we rely on a key property. Our regression model only needs to be linear in its parameters, not its inputs. We can apply nonlinear transformations, like cosine functions or squares, to our inputs before they enter the network. To the linear neuron, these transformed variables simply behave like standard independent features. This snippet shows how we handle the math in PyTorch. We use tensor operations to compute the transformations and concatenate them into a single input structure. This final plot reveals the outcome. Our single linear neuron successfully bends to trace the complex wave of the data. Mapping complex features through a basic linear node allows us to model difficult mathematical functions. It forms the core, scalable building block that all deep neural networks rely on.